You are sitting still right now. Your body has weight. The floor supports you. The air presses gently against your skin. Everything feels continuous, solid, and stable. You assume that objects remain where they are when you are not looking. You assume causes come before effects. You assume that time moves forward, that space exists independently of you, and that your identity persists from one moment to the next. None of these assumptions feel optional. They feel necessary. And yet, at the most fundamental level ever studied by science, every one of them is in question, not metaphorically, not philosophically, mathematically. Modern physics does not merely suggest that reality behaves strangely at small scales. It shows with repeatable experiments and predictive equations that the world you experience may not exist in the way you believe it does. Particles do not have positions until they are measured. Events do not always have clear causes. Time may not be fundamental at all. And the distinction between something happening and not happening may depend on who is observing it. These are not fringe ideas. They emerge from the same theories that make your phone work, that allow satellites to function, that predict experimental results to astonishing precision. The problem is not that these theories fail. The problem is that they succeed while undermining the very idea of an objective, stable reality. This video explores 10 of the most terrifying quantum theories scientists cannot fully explain, not because they are dramatic, but because they work. And because if they are correct, then the world you think you are living in may be a simplified story. Your brain tells itself to survive. 1. Reality does not exist until you look at it. At every moment, you feel surrounded by objects that exist independently of you. The walls, the light, the device you are using to watch this video all appear to persist whether or not you pay attention to them. Yet in quantum mechanics, particles do not possess definite properties until they are measured. Before observation, they exist only as probabilities. This is not a limitation of our instruments, but a feature of the equations themselves. Reality, at its most basic level, seems to wait for interaction before deciding what it is. This idea does not begin as philosophy. It begins in laboratories with carefully controlled experiments and precise mathematics. When physicists describe a particle before it is measured, they do not describe where it is or how fast it is moving. They describe a wave function, a mathematical object that encodes all the possible outcomes of future measurements. Until observation occurs, none of those outcomes is singled out as real. They coexist as potential. You might assume that this uncertainty reflects ignorance, that the particle has a real position you simply do not know yet. Quantum mechanics explicitly rejects this assumption. The theory does not allow you to assign hidden, definite values beneath the probabilities. If you try, the predictions stop matching reality. Experiments confirm this again and again. The particle does not have a position. It has a range of possible positions and nothing more. The unsettling part is not that measurement reveals something. It is that measurement creates something. When you observe a particle, the wave function collapses into a single outcome. A definite position appears. A specific value becomes real. Before that moment, there is no fact of the matter for you to uncover. This raises an immediate question you cannot easily dismiss. What counts as an observation? It is not limited to human eyes. A measuring device is enough. An interaction with the environment is enough. Any process that forces the system to choose between alternatives can play the role of observer. Reality does not wait for consciousness. but it does wait for interaction. Without it, the theory refuses to describe a concrete world. You rely on the assumption that objects continue to exist when unobserved. Quantum mechanics forces you to reconsider what existence means. At small scales, existence becomes conditional. Properties are not permanent features carried through time. They are events that occur at the moment of interaction. This is not just about particles in isolation. Larger systems are constantly interacting with their surroundings, which is why the world appears stable at human scales. But stability emerges from constant observation-like interactions, not from intrinsic definiteness. The solid world you experience may be the result of relentless measurement, not independent existence. If you remove interaction entirely, the theory leaves you with a cloud of possibilities instead of a thing. This challenges the idea of an objective reality that exists fully formed, waiting to be perceived. Instead, reality appears to be participatory. Outcomes depend on the questions asked and the way they are asked. The universe does not simply reveal itself, it responds. You might try to place this strangeness safely at the microscopic level, far removed from everyday life. But the theory does not draw that boundary. The same rules apply everywhere. The difference is not in the laws, but in the scale and complexity of interactions. The discomfort comes from realizing that certainty is not fundamental. Definiteness is not guaranteed. What you experience as a continuous, solid world may be a high-level approximation of something fundamentally unresolved until contact occurs. When you look away from the room you are in, you assume it remains exactly as it was. Quantum mechanics does not affirm this assumption. It suggests that what remains is not a fixed arrangement of facts, but a structured set of possibilities, constantly stabilized by interaction. Reality, in this view, is not a static stage on which events unfold. It is an ongoing process that only takes form when forced to do so. And that means the world you trust may not exist in the way you believe it does until it meets you halfway. 2. Particles can be in two opposite states at once. You assume that something must either be here or there, moving or still, alive or dead. Quantum superposition violates this assumption completely. A particle can occupy multiple mutually exclusive states simultaneously until it is observed. This is not uncertainty in our knowledge, but a literal overlap of possibilities. The world does not choose a single outcome until it is forced to, and until then, contradiction is allowed to exist. This idea feels immediately impossible because it conflicts with how you navigate reality. Your decisions depend on clear alternatives. You step forward or you do not. You speak or remain silent. At the quantum level, these distinctions collapse. A particle can be in two places at once, not metaphorically, but mathematically and experimentally. The equations do not describe a particle switching rapidly between states. They describe a single system occupying all allowed states at the same time. This is not a fringe claim. Superposition is the foundation of quantum mechanics. Without it, the theory fails to predict even the most basic experimental results. When electrons pass through a double-slit apparatus one at a time, they produce an interference pattern that can only be explained if each electron travels through both slits simultaneously. Remove one slit, and the pattern disappears. The behavior changes as if the particle had access to both options until observation removed one. You might assume that the particle secretly chose one path and merely behaved as if it chose both. This explanation is tempting, but it does not survive. Experimental testing attempts to assign hidden, definite states beneath the superposition break the mathematical consistency of the theory. Nature appears to resist being reduced to a single, unseen outcome before measurement. Superposition does not mean that the particle is partially in one state and partially in another. It means the states coexist fully. Each possibility evolves according to the rules of physics, interfering with the others. The result is not ambiguity, but structured contradiction. The unsettling part is not that observation resolves the contradiction. It is that contradiction exists at all. In your experience, opposites cannot coexist. Something cannot be both moving and still. Something cannot be both decayed and undecayed. Yet quantum systems remain suspended between these opposites, following precise mathematical rules until an interaction forces resolution. The universe tolerates inconsistency where you do not. This raises a deeper question about what it means for something to be real. If a particle is in two states at once, which one exists? Quantum mechanics answers by rejecting the question. Reality is not required to choose a single narrative in advance. Multiple incompatible descriptions can all be valid simultaneously. At larger scales, superposition seems to disappear. Objects settle into definite states. You do not observe chairs in two places at once. But this disappearance is not absolute. It is a consequence of interaction with the environment. As systems become more complex, their superposed states rapidly entangle with countless external factors. The overlap becomes impossible to track, and the system appears classical. The contradiction does not vanish, it becomes hidden. This means that the world you experience as stable may be built on unresolved alternatives that never fully collapse, only disperse into complexity. The implications extend beyond physics. If contradiction is allowed at the foundation of reality, then logic itself may be an emergent rule rather than a fundamental one. The consistency you rely on may be a large-scale approximation, not a universal law. When you make a choice, you feel as though one possibility becomes real and the others disappear. At the quantum level, that disappearance is not guaranteed. Possibilities can coexist, interfere, and influence outcomes even when you are only aware of one. Superposition suggests that reality is not obligated to be singular. It can be layered, overlapping, and internally inconsistent, yet still produce the orderly world you inhabit. The discomfort comes from recognizing that what feels impossible to you is not forbidden by nature. It is merely filtered out before it reaches your awareness. Beneath the surface of every definite outcome may be a silent coexistence of opposites that never truly went away. 3. Measurement changes the past. In everyday life, you believe that the past is fixed. Whatever has already happened cannot be altered by choices made in the present. But certain quantum experiments suggest that the way you measure a particle now can determine how it behaved in the past. The sequence of cause and effect becomes unclear, as if reality finalizes its history only after you ask the right question. This idea emerges most clearly in experiments known as delayed choice experiments. You begin with a simple assumption. A particle travels from a source to a detector along a definite path. Either it behaves like a wave, spreading out and interfering with itself, or it behaves like a particle, choosing a single route. Classical intuition insists that this decision must be made at the moment the particle begins its journey. Quantum mechanics refuses this timeline. In delayed choice setups, the choice of how to measure the particle is made after it has already passed the critical point where its behavior would supposedly be determined. You decide whether to measure wave-like interference or particle-like Which path information. only after the particle should have committed to one description. And yet, the results align perfectly with your late decision. If you choose to measure interference, the particle behaves as if it traveled along multiple paths. If you choose to measure a single path, it behaves as if it chose one all along. The measurement does not merely reveal what the particle did, it appears to decide what it did. This is not a trick of timing or experimental error. The mathematics predicts this outcome precisely. There is no moment in the past where the particle can be said to have definitively chosen a behavior independent of how it will later be measured. You might try to rescue causality by arguing that the particle always remained undefined and that measurement simply assigns meaning retroactively. But this explanation does not restore comfort. It replaces a fixed past with a past that is only conditionally real. The problem deepens in quantum eraser experiments. In these setups, information about which path a particle took can be marked and then erased after the particle has already been detected. When the which path information is available, interference disappears. When it is erased, interference reappears, even though the detection has already occurred. It is as if the particle's earlier behavior depends on whether information exists anywhere in the system, even after the fact. The past is not merely unknown, it is unsettled. This does not mean that you can send messages backward in time or rewrite history at will. Quantum mechanics remains internally consistent. What it undermines is the assumption that events have a single, observer-independent narrative. Instead, the theory suggests that events are defined by the total experimental context, including measurements that occur later. Cause and effect become intertwined, not linearly ordered. You rely on a mental model where the present is shaped by the past and moves toward the future. Quantum mechanics allows for descriptions where this ordering is not fundamental. The equations do not privilege a forward-moving time direction. They simply relate correlations between events. What you experience as temporal flow may be an emergent structure layered on top of a deeper, time-symmetric reality. This has unsettling implications for responsibility, memory, and identity. If the past is not fully determined until measured, then what you remember may not be a faithful record of a fixed history, but a stabilized reconstruction. The universe may not store events as completed facts, but as potential narratives waiting to be resolved. When you look at an old photograph, you assume it captures a moment that is permanently gone. Quantum theory suggests that the meaning of that moment depends on present interactions. History becomes less like a record and more like a negotiation. The deeper discomfort lies in the loss of temporal certainty. If cause does not strictly precede effect, then explanation itself becomes fragile. You can no longer assume that understanding what came before will fully account for what comes after. Measurement changing the past does not mean reality is chaotic. It means it is contextual. Events do not exist in isolation. They are woven into a network of relations that extend across time. The past you trust may not be a fixed foundation beneath your feet. It may be a surface that only appears solid because you keep looking at it from the present. 4. Particles communicate faster than light. You are taught that nothing can travel faster than light and that information cannot move instantaneously across space. Quantum entanglement breaks this intuition. When two particles become entangled, their properties remain linked no matter how far apart they are. Measuring one instantly determines the state of the other. No signal appears to travel between them, yet the correlation is immediate, as if distance itself has become irrelevant. This phenomenon is not theoretical speculation. It has been repeatedly demonstrated in laboratories and tested over increasing distances. Entangled particles have been separated by kilometers, by satellites, even between ground stations and orbiting spacecraft. The results remain the same. The correlations appear instantly without delay, regardless of the space between them. You might initially assume that some hidden signal travels faster than light, carrying the information from one particle to the other. Quantum mechanics explicitly forbids this explanation. No usable information is transmitted in the traditional sense. You cannot control the outcome of a measurement to send a message. And yet, the correlation exists before any signal could possibly arrive. This creates a paradox you cannot easily resolve. The universe obeys the speed of light limit for communication, yet behaves as if some connections ignore distance entirely. Einstein famously called this phenomenon spooky action at a distance. His discomfort was not philosophical, it was scientific. Relativity depends on the idea that no influence can propagate instantaneously. Entanglement does not violate the mathematical rules of relativity, but it undermines the intuition that locality is fundamental. Locality is the assumption that objects are only directly influenced by their immediate surroundings. Quantum entanglement suggests that this assumption may be wrong. Two particles can form a single system even when separated by vast distances. Their individual identities blur. Measuring one does not reveal information about the other, it defines it. Before measurement, neither particle has a definite state on its own. Only the relationship between them is defined. The system exists as a whole, not as independent parts. Space separates them physically, but not mathematically. This forces you to reconsider what separation actually means. You rely on distance to define independence. Objects far apart should not affect each other instantly. Quantum mechanics suggests that distance may be secondary, an emergent feature rather than a fundamental barrier. The unsettling implication is that the universe may be deeply non-local. What appears separate at the surface may be unified beneath it. The divisions you perceive may be conveniences of scale, not absolute boundaries. Entanglement also challenges the idea of objective properties. If measuring one particle determines the state of another, then those properties did not exist beforehand. They were not carried across space. They were created through measurement, jointly, as part of a single event. This means that the act of observation does not merely reveal distant facts. It participates in defining them. You might try to comfort yourself by noting that entanglement effects average out at macroscopic scales. You do not experience instantaneous changes in distant objects. But this does not eliminate the underlying structure. It only hides it beneath layers of complexity. At the deepest level, we know how to probe. The universe does not appear to be made of isolated pieces interacting locally. It appears to be a network of relationships that ignore spatial separation. This raises difficult questions about causality. If outcomes are correlated without signals, then cause and effect may not be mediated by space and time in the way you expect. The explanation for an event may not lie in its immediate past or surroundings, but in the structure of the system as a whole. Entanglement suggests that the universe cannot be fully understood by analyzing its parts independently. The whole comes first. The parts are secondary. When you look at the space around you, you see gaps, distances, empty regions between objects. Quantum mechanics suggests that these separations may be superficial. Beneath them, connections persist that do not weaken with distance. The discomfort comes from realizing that your intuition about isolation may be wrong. You may not be as separate from distant events as you believe. The universe may already be more unified than your experience allows you to perceive. Distance still matters to you, but at the quantum level, it may not matter at all. 5. The universe may be splitting around you. Constantly. You experience your life as a single, continuous sequence of events. The many worlds interpretation suggests something far stranger. Every quantum interaction may cause the universe to branch, creating parallel versions of reality where all possible outcomes occur. In this view, you are constantly diverging into countless versions of yourself, each unaware of the others, each believing they inhabit the only real world. This idea begins as an attempt to remove ambiguity from quantum mechanics. In standard descriptions, the wave function collapses when measured, selecting one outcome from many possibilities. The many worlds interpretation rejects collapse entirely. The equations never choose. Instead, all outcomes persist, each in its own branch of reality. Nothing dramatic happens at the moment of branching. There is no flash, no sensation, no signal. From your perspective, reality continues smoothly. You see one result, make one decision, follow one path. But according to this interpretation, every alternative outcome also occurs, just not in the same branch you inhabit. You might imagine this as the universe splitting only during rare dramatic events. The theory does not allow that comfort. Quantum interactions happen constantly, at every scale. If many worlds is correct, branching is not occasional, it is continuous. Each time a particle interacts with its environment, the universe divides into versions where every possible result is realized. These branches quickly become isolated from one another, unable to interfere. From the inside, each branch feels complete and singular. This raises an unsettling question about identity. If countless versions of you exist, each with nearly identical memories up to the moment of divergence, what makes you this one rather than another? There is no privileged branch in the equations. All are equally real. Your sense of being a unique, continuous self may be a local feature of one branch, not a fundamental truth. Identity becomes a pattern that repeats, not a singular thread that persists. The interpretation does not claim that these other versions are accessible. You cannot communicate with them or observe them. They are not hidden nearby. They are separate outcomes of the same underlying process. Their existence is inferred not from direct observation, but from the mathematical consistency of the theory. Many physicists find this deeply unsettling. It multiplies reality beyond necessity. But others argue that it is the simplest interpretation mathematically. It removes the need for special rules about measurement and collapse. The equations describe everything, and nothing ever disappears. This creates a trade-off between conceptual comfort and ontological cost. You either accept that reality selects one outcome through a poorly defined collapse, or you accept that all outcomes exist. The many worlds interpretation also changes how you think about probability. If all outcomes occur, what does it mean to say that something is likely? Probability becomes a measure of how branches are weighted, not a statement about which future will exist. You do not ask which outcome will happen. You ask which outcome you are more likely to experience. This reframes uncertainty as self-location uncertainty. Before an event, you are uncertain which version of yourself you will become, not which outcome reality will choose. The discomfort deepens when you consider moral and emotional consequences. If every possible decision is realized somewhere, then every regret, every failure, every avoided disaster still occurs in another branch. The universe does not forget or forgive. It contains everything. At the same time, every success and every survival also occurs. Catastrophe is never absolute, but neither is triumph. The theory offers no reassurance. It does not privilege hope over despair. It simply asserts that reality is larger than the story you experience. When you look at your past, you believe it contains the only version of events that ever happened. Many worlds suggests it contains only the version you remember. Countless other histories may exist, differing by the smallest details, branching invisibly at every quantum interaction. Your sense of a single, unfolding narrative may be a convenient illusion produced by isolation between branches. If this interpretation is correct, the universe is not a single world with many possibilities. It is a vast collection of worlds where possibility has already been exhausted. And you are not moving through a branching tree. You are embedded in one branch, unaware of how many times the universe has already split around you. 6. Objects do not have definite properties. You assume that an object has a position, a speed, and a trajectory, whether or not you measure it. Quantum mechanics denies this. Properties like position and momentum cannot be simultaneously well defined. They are not hidden values waiting to be discovered. They are created through interaction. Without measurement, the concept of an object having precise attributes may be meaningless. This denial is not philosophical defiance. It emerges directly from the structure of the theory. The Heisenberg uncertainty principle is not a statement about imperfect instruments. It is a limit built into reality. The more precisely you define a particle's position, the less meaningfully you can define its momentum, and vice versa. There is no underlying state in which both are sharp at once. You might imagine that the particle carries exact values you simply cannot access simultaneously. Quantum mechanics does not permit this interpretation. Attempts to assign such hidden properties lead to contradictions with experimental results. Nature does not appear to be withholding information. It appears not to possess it in the first place. Before measurement, a particle is described by a wave function that encodes probabilities for different outcomes. That wave function does not represent ignorance about an actual position or velocity. It represents the full description available. There is nothing beneath it to uncover. This challenges the idea of objects as carriers of intrinsic properties. In classical thinking, an object is defined by what it is, regardless of whether anyone observes it. Quantum mechanics replaces this with a relational picture. Properties exist only in relation to specific measurements. Position is not something a particle has. It is something that emerges when the particle interacts with a measuring apparatus designed to define position. Change the type of interaction, and a different property becomes real instead. This means that the same object can legitimately be described in incompatible ways, depending on how you choose to interact with it. These descriptions are not incomplete. They are mutually exclusive. You rely on the assumption that there is a single, coherent set of facts underlying all possible perspectives. Quantum mechanics suggests that this assumption may be false. Reality may not consist of objects with fixed attributes, but of interactions that temporarily produce attributes. At larger scales, objects appear to have stable properties. This stability arises from constant interaction with the environment. Every collision, every photon absorbed or emitted, acts as a measurement. The environment continuously forces properties into existence, making them appear permanent. But permanence is an illusion of frequency. Properties seem intrinsic only because they are being constantly recreated. This has unsettling implications for identity and persistence. If an object's properties exist only when measured, then what does it mean for something to remain the same over time? Continuity becomes a chain of interactions, not a preserved essence. When you say an object moved from one place to another, you imagine a continuous path through space. Quantum mechanics does not describe such paths. Between measurements, there is no fact about where the object is or how it moves. The trajectory exists only as a retrospective construction linking measurement outcomes. This means that motion, like position, may not be fundamental. It may be a story you tell after the fact to connect discrete events. The discomfort comes from realizing that your everyday picture of objects may be a high-level approximation that breaks down completely at the foundation. The world does not consist of tiny, well-defined things moving along precise paths. It consists of interactions that momentarily give rise to things. This does not make reality arbitrary. The probabilities are precise. The outcomes are consistent. But the underlying ontology is thinner than you expect. Objects, in this view, are not substances with properties. They are nodes in a network of interactions. Their attributes are not carried forward through time. They are continually re-established. When you look away from an object, you assume it retains its characteristics. Quantum mechanics does not guarantee this at the fundamental level. What persists is not a set of properties, but a pattern of potential interactions. The world feels solid because interactions are constant and overwhelming. Remove them, and solidity dissolves into possibility. Definiteness, like so many other features you rely on, may not be a basic feature of reality. It may be something that only appears when the universe is forced to choose. 7. Time may be an illusion. Time feels like the most fundamental feature of existence. Moments pass, causes precede effects. Yet in several quantum gravity models, time does not appear as a fundamental variable. The equations work without it. Instead, time may emerge from more basic relationships, meaning that the flow you experience could be a byproduct of deeper, timeless processes rather than a core feature of reality. You rely on time to make sense of everything. Memory depends on it. Anticipation depends on it. Identity feels anchored to a sequence of moments arranged from past to future. Without time, your experience would collapse into incoherence. And yet, when physicists attempt to unite quantum mechanics with general relativity, time begins to disappear. In quantum gravity approaches, such as the Wheeler-DeWitt equation, the universe is described without any reference to time. There is no variable that tracks change. The equation does not evolve. It simply exists. From this perspective, the universe is not unfolding. It is static. This does not mean nothing happens. It means that change is not fundamental. Instead, what you call change arises from relationships between parts of a larger, unchanging structure. Time is not a river carrying events forward. It is a way of organizing correlations. You experience time because you are embedded within the system, not observing it from outside. From within, certain configurations feel like earlier ones, others like later ones. The distinction comes from memory, entropy, and information, not from a universal clock. This reframes the flow of time as an emergent phenomenon. Just as temperature emerges from the collective motion of particles, time may emerge from the way physical states relate to one another. It feels absolute because you cannot step outside it, but it may not be fundamental. The unsettling implication is that the present moment may not be uniquely real. all moments may exist equally, arranged not along a flowing timeline, but within a static structure. What you experience as now may simply be the configuration your consciousness is currently associated with. This idea echoes in block universe models, where past, present, and future are equally real. The universe becomes a four-dimensional structure with time as another dimension rather than a moving frontier. Nothing comes into being. Nothing passes away. Everything simply is. Quantum mechanics adds another layer of discomfort. If time is not fundamental, then the order of events may not be either. Certain quantum processes do not have a well-defined causal order. Event A does not clearly happen before or after event B. The distinction becomes context-dependent. You rely on causality to explain why things happen. If time emerges rather than governs, causality becomes approximate. It works well at large scales, but it may not hold universally. This raises questions about free will and agency. If the future already exists in the same sense as the past, then choice may not be about creating new outcomes, but about experiencing one path through a pre-existing structure. The feeling of decision remains, but its role changes. The discomfort is not that these ideas remove meaning. It is that they remove privilege. The present loses its special status. The now you inhabit is no longer the edge of reality advancing forward. It is just one slice among many. You feel time passing because your memory accumulates records in one direction. Entropy increases. Information disperses. These processes create an arrow of time from within the system, but the arrow may not be fundamental. It may be a statistical tendency, not a law. At the deepest level, the universe may not care about before and after. It may only care about consistency between relationships. When you say something happened long ago, you assume it is gone. Quantum gravity suggests it may be as real as anything else, just not accessible from your current perspective. The separation is experiential, not ontological. Time may feel unavoidable because your consciousness is built to track change. But the structure generating that change may not include time at all. If time is an illusion, it is not a trivial one. It is the lens through which you perceive existence. And like any lens, it shapes what you can see while hiding what lies beyond it. 8. The observer cannot be removed from reality. Classical physics assumes that observers can study the universe without affecting it. Quantum mechanics does not allow this separation. The act of observation is not passive. It plays a role in determining outcomes. This raises an unsettling question. If reality depends on observation, what exactly counts as an observer? And where do you draw the boundary between the system and the one measuring it? You are accustomed to thinking of yourself as external to what you observe. You look at the world, and the world continues on its own. In quantum mechanics, this distinction fails. Observation is not a window. It is an interaction, and interactions change the system being studied in fundamental ways. When you measure a quantum system, you are not simply reading off a pre-existing value. You are forcing the system to take on a definite state. The theory does not describe what the system was like before measurement in the same terms. The measurement is not an afterthought. It is part of the physical process. This creates what is known as the measurement problem. Quantum mechanics gives precise rules for how systems evolve when unobserved, and precise rules for the probabilities of outcomes when observed. What it does not clearly define is where observation begins. There is no sharp line in the equation separating the quantum world from the classical one. You might try to place the boundary at the measuring device. But measuring devices are made of atoms, and atoms obey quantum laws. You might push the boundary to the environment, but the environment is also physical. Wherever you draw the line, the theory itself does not acknowledge it. This leads to an unsettling conclusion. The distinction between observer and observed may not be fundamental. It may be a practical convenience rather than a feature of reality. From this perspective, you are not standing outside the universe watching it unfold. You are part of the same quantum system you are attempting to describe. Your observations are interactions within that system, not external probes. This does not mean that your consciousness directly shapes reality in a mystical sense. Quantum mechanics does not require awareness, intention, or thought. It requires interaction. But it does require that some process selects a definite outcome from many possibilities. The discomfort arises when you realize that the theory does not specify what kind of process this must be. It does not say when a quantum possibility becomes a fact. It only gives probabilities for outcomes once the process has occurred. Some interpretations attempt to remove the observer entirely by treating all interactions as quantum and allowing no collapse. Others accept collapse, but leave its mechanism undefined. None fully restore the classical idea of a detached observer. You rely on the assumption that reality has a definite state, regardless of whether anyone is watching. Quantum mechanics does not support this assumption. It suggests that definiteness is contingent, arising only through specific interactions that cannot be cleanly separated from the rest of the world. This blurs the boundary between knowledge and existence. In classical physics, knowing something does not change it. In quantum mechanics, the act of gaining knowledge is inseparable from the physical process that creates the outcome. The implication is not that reality is subjective in a personal sense. It is that objectivity itself may be relational. Facts exist relative to interactions, not in isolation. When you observe a system, you become correlated with it. Your measuring device records an outcome. Your memory stores it. These correlations define what is real for you. Another observer, interacting differently, may legitimately describe a different reality. This does not lead to contradiction because observers cannot freely compare all descriptions. But it does mean there is no single, absolute account of what happened that exists independently of all observers. The unsettling realization is that the universe does not offer a view from nowhere. Every description is from within. You are not a passive witness to reality. You are woven into its fabric. The very act of asking a question about the world changes the set of possible answers, and there may be no deeper level at which the observer can be cleanly removed, leaving a fully defined world behind. 9. Particles. Follow paths that do not exist. When you imagine motion, you picture a path through space. Quantum particles do not move this way. In experiments like the double slit, particles behave as if they explore all possible paths simultaneously. The path you eventually observe is not the one it traveled, but the one that remained after interference canceled out the others. Motion becomes a statistical artifact rather than a physical journey. You rely on trajectories to understand movement. An object leaves one position, passes through intermediate points, and arrives at another. This picture is so deeply ingrained that it feels inseparable from reality itself. Quantum mechanics dismantles it at the foundation. In the path integral formulation of quantum theory, a particle does not take a single route from one point to another. Instead, every possible path contributes to the outcome. Straight lines, curved paths, even wildly indirect routes all play a role. Each path carries a mathematical weight, and these contributions interfere with one another. The path you observe is not selected in advance. It emerges as the result of cancellation. Most paths interfere destructively, eliminating one another. A small subset reinforce each other, producing the behavior that resembles a classical trajectory. This means the classical path is not fundamental. It is a residue left behind after an immense superposition of possibilities has been filtered through interference. You might try to imagine the particle rapidly sampling different routes, but this image fails. The theory does not describe motion as a sequence of attempts. It describes a single process in which all paths are considered at once. Time itself becomes part of the calculation, not a stage on which motion unfolds. The double-slit experiment makes this especially clear. When a particle passes through two slits, it produces an interference pattern even when sent one at a time. This pattern cannot be explained by a particle choosing one slit and then traveling along a definite path. The interference requires that the particle behave as if it went through both slits and explored all possible trajectories beyond them. When you attempt to detect which slit the particle passed through, the interference disappears. The available paths collapse into a single class. Motion becomes classical again, not because the particle suddenly behaves differently, but because the conditions no longer allow interference. This suggests that paths are not properties of particles. They are consequences of the questions you ask. Ask about position along the way, and you force the particle into a narrative of motion. Do not ask, and the narrative dissolves. The unsettling implication is that motion itself may not be fundamental. What you experience as continuous movement may be a macroscopic approximation of something far less intuitive. Between measurements, there is no fact of the matter about where the particle is or how it gets from one place to another. This challenges the idea of space as a container filled with moving objects. If particles do not trace paths, then space may not be populated by trajectories at all. It may be a framework for relationships between events, not a medium through which things travel. At large scales, the illusion of paths is reinforced by constant interaction. Objects are continuously measured by their environment. Collisions, photons, and forces force paths into existence, but this does not make paths fundamental. It makes them persistent. You experience your own motion as a continuous journey through space. Quantum mechanics suggests that this experience is constructed from countless interactions that suppress alternative possibilities. The smoothness you perceive is the result of overwhelming interference cancellation. This reframes movement as a statistical outcome rather than a literal journey. Objects appear to move because the probabilities align in ways that mimic trajectories. The discomfort lies in realizing that the path you imagine may never have existed. What you call motion may be a story told after the fact, connecting discrete interactions into a coherent narrative. If particles do not follow paths, then the universe is not a collection of objects traveling through space. It is a web of events connected by probability, and the path you trust may be nothing more than the one that survived when all the others erased each other. 10. Causality is not guaranteed. You rely on cause and effect to make sense of the world. Quantum theory allows situations where causality is not well defined. Some processes cannot be said to have a clear cause or a clear effect. In certain formulations, events influence each other in ways that do not fit into a single directional timeline, challenging the assumption that reality must follow a logical sequence. Causality feels fundamental because it underpins understanding. You assume that one event produces another, that effects follow causes in an orderly fashion. Your memory, planning, and reasoning are built on this principle. But in quantum mechanics, and especially in advanced formulations, combining quantum theory and relativity, this linearity is not guaranteed. Certain experiments suggest that two events can become entangled in a way that the order in which they occur cannot be determined. In these indefinite, causal order scenarios, event A and event B influence each other without a definite before and after relationship. The traditional arrow of time, so central to your perception of reality, becomes ambiguous. This is not merely a mathematical curiosity. Quantum switch experiments have demonstrated that operations can be applied in superpositions of different orders. The outcome depends on both events, but there is no unique temporal sequence. The universe allows events to be both before and after each other in a sense that classical intuition cannot reconcile. You might attempt to restore comfort by assuming that causality must exist somewhere at a deeper level. Quantum mechanics resists this assumption. These processes are fully consistent with the mathematical framework, yet they defy embedding into a single causal chain. Nature does not guarantee that every effect can be traced back to a clear, singular cause. The unsettling implication is that explanations themselves may be conditional. Your attempts to account for why something happens could be limited by the structure of reality. Sometimes, there is no simple narrative linking event to outcome. There is only correlation without a definitive origin. This challenges deeply ingrained notions of predictability. If cause is not fundamental, then the rules you rely on to infer the future from the past are approximate, emergent, and sometimes context-dependent. Quantum indeterminacy already introduces uncertainty, but indefinite causality removes even the framework for ordering uncertainty. Consider decision-making. You feel that one choice leads to another, producing a chain of consequences. At the quantum level, such chains may not exist in a singular order. Outcomes can be intertwined in ways that cannot be decomposed into sequential steps. The universe does not promise a narrative you can fully reconstruct. This also reframes your understanding of time itself. If cause does not always precede effect, the arrow of time may be emergent rather than fundamental. Events could be connected outside the linear structure you experience, with temporal order arising only as a macroscopic approximation. The philosophical implications extend to agency and responsibility. If effects are not reliably traceable to causes, then the relationship between actions and consequences becomes more subtle. The universe may contain correlations that are real, but not reducible to the sequence you expect. Even at the scale of everyday life, the notion that reality is fully ordered is called into question. The apparent consistency of events is a consequence of overwhelming interactions and emergent classicality, not a guarantee embedded in the laws themselves. Beneath the surface, the connections between events may be far more fluid than your intuition allows. Causality, which feels like the backbone of reality, may be a convenient approximation rather than an absolute rule. It works because most systems are entangled with their environment, stabilizing outcomes in predictable sequences. But in principle, there is no requirement that every event must have a single, identifiable cause. This opens a disquieting possibility. The universe is not obliged to behave logically in the way you expect. Correlations can exist without a story, without sequence, without origin. Some outcomes simply are, connected only through patterns of relation, not through linear chains of cause and effect. Your reliance on causality may give the impression of a coherent world. Quantum theory warns that this coherence is emergent, fragile, and provisional. At the deepest levels, reality is not obliged to answer to the narrative structures your mind imposes. Cause and effect, it seems, are privileges of perception, not guarantees of existence. 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 11. The vacuum is not empty. You imagine empty space as a void, a background in which events occur. Quantum field theory shows that even the vacuum seethes with activity. Particles appear and disappear spontaneously. Energy fluctuates. What you call nothing is, in fact, unstable. Existence does not require something to trigger it. It can emerge from the structure of reality itself. The vacuum, in classical thought, is absence. You picture a black emptiness, an infinite stage on which matter and energy perform their acts. Quantum mechanics shatters this assumption. Even in regions devoid of matter, the fields that constitute the universe are never at rest. They vibrate, fluctuate, and interact, creating a restless landscape of potentiality. Virtual particles blink into existence and vanish without warning. They do not move along trajectories or persist in time as ordinary particles do. They exist fleetingly, allowed by the uncertainty inherent in quantum energy. These ephemeral entities are not errors or artifacts of theory. Their effects are measurable. The Casimir effect, for instance, produces a detectable force between uncharged metal plates solely because of vacuum fluctuations. The void pushes back. It is never inert. Energy itself is unstable in the vacuum. Even if a region appears empty, the fields have a lowest energy state known as the vacuum state, but it is not zero. Fluctuations ensure that nothing is ever truly at rest. These quantum jitters are not minor. They are the foundation of forces, the seed of particle creation, and, according to some cosmological models, the origin of the universe itself. You might feel comforted by the idea that existence requires a cause. Quantum field theory challenges this intuition. The vacuum itself can generate particles without an external trigger. In a sense, being is intrinsic to the structure of reality. Nothing does not exist as a stable, eternal absence. Nothingness is provisional. Existence seeps through it spontaneously. This activity is continuous, relentless, and indifferent to observation. You cannot step into a quantum vacuum and find calm. The fluctuations are woven into the fabric of space-time. Even empty space exerts pressure, carries energy, and contributes to the dynamics of the universe. The vacuum is not a passive backdrop, but an active participant in reality. The implications are profound. If nothing is unstable, then the boundary between existence and non-existence is blurred. Objects appear and vanish at the smallest scales, and the apparent permanence of the world arises from the overwhelming aggregation of countless fluctuating events. Stability, like motion, is emergent rather than fundamental. In cosmology, this restlessness may have been decisive. The early universe could have emerged from vacuum fluctuations. Inflationary models suggest that quantum jitters in empty space expanded, giving rise to the structures you now perceive as galaxies, stars, and planets. The universe itself may have been born from nothing, but the nothing in question is not the void of classical thought. It is a boiling, fertile medium, pregnant with potential. Even at the scale of your everyday life, the vacuum has subtle effects. It influences the energy levels of atoms, contributes to forces between particles, and affects decay rates. What you call empty space is never silent. It hums with possibilities, with events that could occur even if they never materialize in your experience. This challenges your intuition about stability and existence. The world you perceive as solid, continuous, and inert rests upon a foundation that is anything but. Beneath the apparent calm lies a restless, fluctuating quantum reality, indifferent to expectation and unconstrained by permanence. The vacuum reveals that nothing is ever truly inert. What you consider emptiness is in fact a dynamic, seething medium from which existence continually emerges. Reality does not wait for cause or observer. It generates, persists, and transforms spontaneously, even where you perceive absence. In this view, the void is not the absence of being. It is the source of it. Existence, at its most fundamental level, is spontaneous, ubiquitous, and unavoidable. The universe, it seems, never truly sleeps. 12. Probability is more fundamental than reality. In your daily life, probability describes ignorance. You flip a coin because you do not know how it will land. In quantum mechanics, probability is not a placeholder for missing information. It is fundamental. The universe does not know what will happen next until it happens. Certainty may not exist at the deepest level, only likelihoods that solidify when observed. You assume that the world contains definite facts, even if you cannot access them. A coin lands on heads or tails regardless of whether you are looking. A tree falls with or without a witness. Classical probability reflects your lack of knowledge, not the indeterminacy of events themselves. Quantum mechanics overturns this intuition entirely. In the quantum realm, the outcome of an event is not merely unknown, it is genuinely undefined. Particles do not possess predetermined properties awaiting discovery. They exist in a superposition of possibilities, each assigned a probability by the wave function. Before measurement, no single outcome is realized. The universe itself exists in a state of potentiality. This is not an artifact of limited technology. Experiments consistently show that attempts to assign hidden variables, underlying deterministic rules, fail. Bell's theorem and the associated experiments demonstrate that reality cannot be both local and deterministic. The probabilistic nature of quantum events is baked into the structure of the world. Likelihoods are primary, certainties are emergent. Probability shapes reality itself. When a measurement occurs, one possibility becomes actualized. The collapse of the wave function transforms potential into fact. Until this moment, the world is fundamentally undecided. The universe is a landscape of probabilities rather than a stage of predetermined outcomes. This has unsettling implications for how you understand existence. If probability is primary, then reality is not a fixed sequence of facts waiting to be uncovered. Reality is a tapestry woven from the interplay of potential outcomes, a dynamic pattern that only crystallizes in response to interactions. The world you perceive as solid, determinate, and continuous is a high-level approximation, not a fundamental truth. Even macroscopic events are underpinned by these probabilistic processes. While interactions with the environment tend to suppress quantum indeterminacy, producing the appearance of determinism, the underlying foundation remains probabilistic. Every classical outcome is built upon countless micro-decisions, each governed by the irreducible uncertainty of the quantum domain. You might try to cling to the idea of absolute cause and effect. Quantum mechanics challenges this. The probabilities assigned to each potential outcome do not guarantee that a single narrative will unfold. They only provide the statistical framework from which a particular history emerges once observed. In this sense, likelihoods precede reality. They form the scaffolding upon which fact is constructed. This perspective destabilizes your intuitive sense of predictability. You assume that with enough knowledge, you can foresee the future. Quantum theory insists that some aspects of the future are intrinsically unknowable until they occur. The universe does not decide in advance. It explores possibilities and allows one to solidify. Probability, then, is not a tool for humans. It is a feature of existence itself. It is the medium through which reality emerges. Certainty, continuity, and identity arise only because interactions collapse a field of potentialities into a pattern coherent enough to sustain perception. The universe is not a machine with fixed outcomes. It is a web of possibilities, a system in which events are defined by the interplay of likelihoods. What you experience as reality is the product of selection among probabilities, stabilized by observation and interaction. In this view, probability is more real than the world you think you inhabit. Facts, objects, and events are temporary manifestations. Beneath them lies a vast sea of potential, a probabilistic substratum that never rests, never commits, and only occasionally becomes what you call real. Certainty may be comforting, but it is provisional. Probability is primordial. It is the language in which the universe is written, the rule from which existence itself emerges, and the foundation upon which the illusion of a definite reality is built. 13. The universe computes itself. Some interpretations suggest that the universe behaves like a vast quantum computation. Physical processes resemble calculations, with reality evolving through transformations of information. If this is true, then existence may be less about matter and more about the processing of abstract states. The physical world becomes a manifestation of an underlying informational structure. You are accustomed to thinking of the universe as composed of objects, particles, atoms, stars, galaxies, that interact according to physical laws. These laws govern motion, energy, and forces. But what if the substance of reality is not particles or fields at all, but information? In this view, everything you perceive is the output of an ongoing computation, a series of transformations that determines what is observed and experienced. In quantum mechanics, the notion of information is already fundamental. The state of a system is described mathematically by a wave function, which encodes all possible outcomes and their probabilities. Evolution of the system follows precise rules, as if an algorithm were executing step by step. Measurement transforms the state, collapsing possibilities into a definite outcome. From this perspective, observation is not just passive recording. It is a computation that produces a particular realization from the set of potentialities. If the universe is a computation, then space, time, and matter are emergent phenomena. They are not fundamental ingredients of existence, but consequences of deeper informational rules. Particles and fields become expressions of information being processed according to underlying algorithms. The physical world you inhabit is, in effect, the output of a computation that is constantly running at scales and speeds far beyond direct perception. This interpretation shifts your sense of reality. You assume that matter exists independently and obeys laws imposed externally. But if existence is informational, then the universe is self-referential. It computes its own evolution from within, with no external observer, no underlying hardware beyond the rules it implements. Everything, energy, space, causality, is an emergent property of the ongoing calculation. Quantum phenomena reinforce this perspective. Superposition, entanglement, and interference resemble processes in a computational system. A particle in a superposition explores all possible states, much like a parallel computation evaluating multiple possibilities. entangled particles coordinate instantaneously across space, as if linked through a shared information channel. The apparent strangeness of quantum mechanics may reflect the underlying informational nature of reality, rather than a breakdown of physics. Even macroscopic objects can be understood in this way. Their apparent stability emerges from the continuous processing of information across enormous numbers of constituent particles. Classical behavior arises when the computation produces overwhelmingly probable patterns, masking the underlying probabilistic and algorithmic structure. Reality is deterministic in its rules, yet indeterminate in its outcomes until processed. The philosophical implications are unsettling. You are not simply occupying a world, you are embedded within a process. Your experiences, thoughts, and observations are not separate from the universe's operation. They are part of the computation. Your consciousness may be a pattern emerging from informational processing, no more separate from reality than the particles whose states you perceive. This perspective also challenges notions of fundamentality. If information is primary, then asking what things are made of may be meaningless. Particles, forces, and fields are secondary, emergent features of computation. The substrate of reality is abstract, a network of relationships and transformations that produces the phenomena you call physical. The universe as computation implies that existence is relational, dynamic, and algorithmic. Reality is not a collection of things following laws. It is a system calculating itself, continuously generating the structures, events, and interactions that you experience. The laws of physics may themselves be emergent rules within this deeper informational framework. In this view, the solidity of matter, the flow of time, and the linearity of causality are all results of an underlying computation. What appears permanent and deterministic is only a pattern produced by repeated processing. Beneath the surface, reality may be an intricate algorithm, endlessly iterating, infinitely parallel, and indifferent to the comfort of intuitive understanding. To inhabit this universe is to be both observer and participant in an immense computation, a process whose complexity exceeds comprehension. Reality is less a fixed stage and more a continuous calculation, in which you are a node, a pattern, and an output simultaneously. The universe computes itself, and in doing so, it creates everything you perceive as real. 14. You may be entangled with the world around you. Entanglement is not limited to tiny particles in laboratories. In principle, any interacting systems can become entangled. This means that you are not entirely separate from your environment at the quantum level. Your state may be subtly linked to countless other systems, blurring the line between self and world in ways that classical intuition cannot capture. You perceive yourself as distinct, a coherent individual occupying a defined space. The chair you sit on, the air you breathe, the light illuminating the room, all of these seem external, separate from the experience of being you. Entanglement challenges this intuition. At the quantum level, interactions create correlations that cannot be explained by independent properties alone. Systems that interact can no longer be fully described in isolation. Their states are entwined. Even a simple particle interacting with its environment becomes part of a larger entangled system. The environment, in turn, interacts with more particles, which interact with others, cascading into networks of correlation. If this principle extends to macroscopic scales, it suggests that you, your body, and the world around you form a web of subtle quantum connections. The boundaries you take for granted between inside and outside, self and other, may be less absolute than they appear. You might think entanglement requires delicate isolation, but the principle does not impose a size limit. Theoretically, any systems that interact and maintain coherence for sufficient time can share entangled states. The reason you do not consciously perceive this entanglement is that interactions with the environment tend to rapidly decohere quantum correlations. Nonetheless, the underlying connections remain, hidden beneath the classical surface. This has profound implications for identity. You think of yourself as a distinct entity with intrinsic properties. But if your quantum state is entangled with your surroundings, your state cannot be fully described independently. Some aspects of who you are may be relational, existing only in context with the larger system of which you are part. Individuality becomes emergent, not absolute. Consider how this perspective affects causality and influence. If parts of the universe are entangled, local changes may carry correlations that are not mediated by conventional forces or signals, while macroscopic effects remain constrained by classical physics. The foundational reality is a network of potential influence where separation is not fundamental. You are, in some sense, already connected to distant systems through correlations that exist independently of observation. Your thoughts, sensations, and bodily processes emerge from countless interacting particles. Each interaction generates entanglement with your immediate surroundings. Photons reflecting from surfaces, electrons moving in your neurons, molecules colliding in the air. All of these contribute to the continuous formation of correlations between you and the environment. In principle, your experience is inseparable from the web of interactions in which you participate. The unsettling consequence is that the classical picture of a discrete self may be an approximation. The boundaries of individuality are a high-level emergent property of decoherence and complexity. At the quantum level, these boundaries dissolve into networks of entangled relations. You are not entirely contained within your body. Your state is partially defined by the environment and its countless interacting components. Even more striking, this entanglement is universal. Every interaction in the cosmos contributes to an interconnected structure of correlations. The objects, events, and systems you consider separate are fundamentally linked at the level of potential outcomes. Reality itself is a vast entangled web in which every node subtly influences and reflects every other. Entanglement reframes the very concept of isolation. Solitude, separation, and independence are emergent phenomena. At the deepest level, your existence is a relational pattern, inseparable from the myriad interactions that shape it. You are not merely in the world is partially in you. To recognize this is to confront a subtle but profound unease. The intuitive distinction between self and environment, between observer and observed, may be an illusion maintained by decoherence. At the fundamental level, the universe does not consist of isolated objects, but of networks of interdependent, entangled states. You, like everything else, are woven into this invisible tapestry, inseparably connected to the world around you. 15. Identity may not be continuous. You feel like the same person from one moment to the next. Quantum theory raises the possibility that continuity is an approximation. If reality updates itself probabilistically, then the persistence of identity could be an emergent narrative rather than a guaranteed feature. What you call yourself may be a sequence of closely related states rather than a single, enduring entity. You experience memory as a continuous thread, linking past, present, and anticipated future. You assume that the you who remembers breakfast is the same you who plans the evening. Quantum mechanics challenges the assumption that continuity is fundamental. At the smallest scales, particles and fields are probabilistic, fluctuating, and relational. The systems that compose your body and brain are constantly interacting, exchanging energy, and updating their states. Each update is probabilistic, not predetermined. Identity, in this sense, is not an absolute. Your sense of self arises from the coherence of these fluctuations over time. Neural patterns, bodily states, and memories align sufficiently to give the impression of a continuous self. Yet beneath this emergent coherence, the states that constitute you may be discrete and probabilistically related rather than fixed and persistent. Consider your brain as a network of entangled quantum systems. Every thought, sensation, and perception emerges from interactions among these systems. Each update, each firing of neurons, each chemical reaction represents a probabilistic event. In principle, if these updates are fundamentally quantum in nature, then the identity you experience is a series of transient states, stitched together by coherence and redundancy. The persistence of you is maintained by the improbability of drastic divergence, not by any fundamental continuity. This perspective reframes your understanding of personal history. The you who experienced childhood is not a single, unbroken entity, but a set of probabilistically related states that evolve into the you of today. Memories are not stable records of an enduring self. They are patterns reconstructed from current states that correlate strongly with past configurations. Continuity is inferred, not guaranteed. The probabilistic updating of reality implies that identity is relational. You exist in the context of interacting systems, your body, your environment, and, at larger scales, your social and informational networks. Your state is partially defined by these interactions. If the underlying processes of reality are not strictly deterministic, then the borders of self are flexible, provisional, and context-dependent. This raises an unsettling possibility. The you reading these words may not be fundamentally the same as the you a second from now, except insofar as the probabilistic correlations are strong enough to preserve coherence. The illusion of continuous identity relies on stability emerging from a vast network of interactions and redundancies. Remove the coherence, and the notion of a persistent self dissolves. Philosophically, this challenges notions of moral responsibility, memory, and agency. If identity is not continuous, then what does it mean to be the same person across time? Decisions and consequences may be experienced by one version of a self, while other probabilistic branches exist with diverging outcomes. Continuity is practical, emergent, and functional, not guaranteed by the underlying physics. Even at a macroscopic scale, the persistence of identity is approximate. Bodies maintain form, memories are reconstructed with fidelity, and patterns of behavior appear stable. Yet all of these are emergent consequences of countless probabilistic updates, not a reflection of any absolute, underlying self. Ultimately, identity may be less like a single river, flowing unbroken, and more like a sequence of overlapping snapshots, each probabilistically correlated with the previous one. You experience this continuity as a seamless narrative, because the likelihood of drastic divergence is exceedingly low, but the foundation itself is fragile, constructed from patterns rather than substance. If this is correct, your self is not a fixed entity traveling through time. It is a temporary pattern of coherence, emergent from probabilistic updates, existing as long as the correlations hold, and changing in subtle ways with every interaction. The continuity you take for granted is a remarkable but provisional feature of a fundamentally indeterminate universe. 16. Space may be discrete, not continuous. You picture space as a smooth expanse. Some quantum gravity theories suggest that space itself is made of indivisible units. Below a certain scale, the concept of distance may break down entirely. If space is granular, then motion, geometry, and locality are emergent, not fundamental. Your intuition treats space as an unbroken continuum, a stage on which events unfold. Every point seems connected to its neighbors in an infinitely divisible way. Yet, when physicists attempt to merge quantum mechanics with general relativity, this picture begins to crumble. The smooth continuum may be an approximation, accurate at scales we experience, but inadequate at the Planck scale, where quantum effects dominate. Loop quantum gravity, one leading approach, describes space as a network of discrete loops, forming a granular fabric. Areas and volumes are quantized, meaning there is a smallest possible unit of length and space itself cannot be subdivided further. Between these units, the concept of distance loses meaning. The familiar idea of motion through a continuous medium becomes a construct emerging from a fundamentally discrete structure. If space is made of indivisible quanta, your perception of continuity is an emergent phenomenon. Classical geometry, Euclidean or curved, arises from the large-scale averaging of countless discrete units. The straight line you imagine may be nothing more than a convenient approximation, a macroscopic illusion created by the collective behavior of a fundamentally granular reality. Locality, the principle that objects affect only their immediate surroundings, is also called into question. At the smallest scales, interactions may not respect conventional spatial separation. Entanglement and quantum correlations can link regions that, from the perspective of emergent geometry, are distant. Space is no longer a barrier, but a secondary feature, arising from underlying connections between discrete quanta. The implications for motion are profound. You picture a particle tracing a path through continuous space. If space is discrete, there are no points in between the quanta. Motion is not a smooth traversal, but a sequence of hops from one unit to the next. Classical trajectories emerge only when the granularity is averaged over large scales, producing the illusion of continuous flow. Even time may be affected. Some theories suggest that if space is quantized, time might also be granular, with events occurring in discrete steps rather than a seamless flow. The familiar sensation of continuous change could be a byproduct of averaging over these microscopic discontinuities. The universe may tick at a fundamental level, and your perception of smooth progression is merely a high-level emergent pattern. Geometry itself, the bedrock of your understanding of distance, curvature, and shape, becomes relational rather than absolute. A sphere, a plane, or a line exists only as a statistical consequence of many quanta arranged in particular patterns. The precise smoothness you assume in everyday life is an artifact of scale, not a guarantee of fundamental structure. Your notions of inside and outside, near and far, begin to dissolve. Space is no longer a continuous backdrop, but a mosaic of discrete nodes. Objects interact through the network of these nodes, and the familiar intuition of adjacency or separation is emergent. The granularity is invisible at human scales, yet it underlies every interaction, every measurement, every perception. The unsettling realization is that the fabric of reality may be pixelated at the smallest scales. The continuous world you inhabit is built from discrete units whose relationships produce the appearance of smoothness. Distance, motion, geometry, and locality, the features you take for granted, may be emergent, provisional, and context-dependent. If space itself is discrete, then the universe is fundamentally digital at its core, not analog. Your sense of flowing space, continuous trajectories, and uninterrupted geometry is a product of averaging over countless quanta. Beneath the surface, reality is a lattice of fundamental units, granular and discrete, shaping the world you experience in ways you cannot directly observe. In this framework, the smoothness of the cosmos is an illusion, a mirage of scale. Motion, continuity, and locality are emergent patterns on a substrate that is not continuous, not infinitely divisible, and not constrained by classical intuition. Space, as you perceive it, is a coarse-grained approximation of a deeply granular, discrete reality. 17. The laws of physics may not be fixed. You assume that the laws governing reality are constant. Some theories propose that they could change, or that what you observe as laws are statistical regularities arising from deeper dynamics. Stability becomes a temporary condition rather than a permanent rule, and the predictability you rely on may be contingent rather than absolute. From a young age, you are taught that the universe obeys consistent rules. Gravity pulls, light travels at a fixed speed, and energy is conserved. These laws are assumed to hold everywhere and everywhen, providing a foundation for understanding, prediction, and planning. Yet, at the frontiers of theoretical physics, this assumption is no longer unassailable. Some cosmological models suggest that what we call the laws of physics may emerge from deeper, more fundamental structures. They are not fixed axioms etched into reality, but patterns that arise statistically from the interactions of underlying entities. In this view, constants such as the speed of light, Planck's constant, or the fine structure constant may be emergent properties of a larger framework rather than immutable features of the cosmos. The idea that laws might vary across space or time is not purely speculative. Certain multiverse models suggest that regions of the universe could operate under different physical rules. What you perceive as universal constants may be local regularities, stable only within the domain you inhabit. Beyond your horizon, the behavior of matter and energy could be radically different, with forces, particles, and interactions that defy all expectations. Even within your own observable universe, laws may not be permanently fixed. Some quantum cosmology proposals describe a dynamic landscape of possible vacua, each with its own effective laws. Transitions between these vacua could alter the constants or interactions in subtle or dramatic ways. What appears permanent today might have been different in the past or could shift in the future. Stability becomes contingent, and the framework you rely on may be provisional. The implications for predictability are profound. Science relies on the assumption that repeated experiments produce consistent results. If laws themselves are emergent or variable, reproducibility is approximate, not guaranteed. Patterns you take for granted, orbital mechanics, chemical reactions, thermodynamic processes, are stable only because the underlying dynamics have produced a temporary, coherent structure. They are not guaranteed by any absolute necessity. Even the most foundational principles, such as conservation laws, may be contingent. In certain scenarios, symmetries that enforce conservation could be emergent rather than fundamental. The rules of the game, rather than being fixed, are the outcome of a higher-level system whose parameters are probabilistic or variable. The universe may be more like a self-organizing computation than a preordained machine. This perspective destabilizes assumptions about causality, identity, and permanence. If the laws of physics can change, then any prediction, no matter how confident, rests on the assumption that the framework generating those predictions remains constant. Even your understanding of time, space, and matter is provisional, dependent on statistical regularities that may not be eternal. the philosophical and existential weight of this idea is unsettling. You trust that the universe is orderly, that events follow reliable patterns, and that the knowledge you accumulate corresponds to enduring truths. If the laws themselves are emergent, your sense of security, control, and comprehension becomes contingent. Reality is less a fixed system to be understood, and more a dynamic, evolving structure in which stability is temporary and predictability is provisional. Even at scales you can perceive, the order you experience, the rise and fall of objects, the flow of energy, the behavior of forces, is a manifestation of deep patterns maintained by underlying interactions. The universe operates consistently because its deeper dynamics favor certain configurations. But this consistency may be a statistical accident, a temporary stability in a larger, fluctuating cosmos. In this view, what you call the laws of physics are not ultimate rules, but emergent features of a complex, probabilistic system. Predictability, stability, and permanence are privileges of scale and context, not guarantees of existence. At its deepest level, the universe may be fluid, dynamic, and mutable, with laws that emerge, persist for a time, and perhaps dissolve into new patterns, leaving the very fabric of reality more contingent than you have ever imagined. 18. Observation may create reality, not reveal it. Classical science treats observation as discovery. Quantum mechanics suggests creation. The properties you measure may not have existed prior to measurement. This shifts the role of science from uncovering a pre-existing world to participating in the generation of outcomes, raising profound questions about objectivity. You assume that the universe possesses definite properties, independent of whether you look. A table exists with fixed dimensions, a photon has a defined trajectory, and an atom contains a nucleus surrounded by electrons, regardless of whether anyone observes them. This assumption underpins the classical worldview. Science describes, rather than influences, reality. Quantum mechanics challenges this deeply. Experiments, beginning with the double slit and continuing through delayed choice and quantum eraser setups, reveal that the act of measurement is not passive. Particles do not merely exist with properties awaiting detection. Their measurable attributes, position, momentum, spin, become defined only through the interaction of measurement itself. Before observation, they are not just unknown, they are undefined, residing in a superposition of possibilities. Consider a photon passing through a double-slit apparatus. Until you detect it, it behaves as though it simultaneously takes both paths, producing an interference pattern. Once you attempt to measure which slit it went through, the pattern collapses into a single outcome. Observation did not merely reveal the photon's path, it determined it. The act of measurement participates in the creation of reality, converting potentiality into actuality. This phenomenon extends beyond microscopic particles. In principle, any quantum system with sufficient coherence can exhibit similar behavior. The implications reach into the macroscopic world as well. The stability and definiteness you perceive emerge from the aggregation of countless quantum interactions, each of which depends on observation, environment, or decoherence processes. The world appears fixed because so many events collectively reinforce particular outcomes, but at the fundamental level, the act of defining properties is inseparable from the act of interaction. The shift from observation as discovery to observation as creation destabilizes notions of objectivity. Science is often understood as the neutral measurement of an independent reality. Quantum mechanics forces a reconsideration. The observer is part of the system. Knowledge is not merely a passive reflection of a pre-existing world. it participates in shaping it. Measurement choices influence the outcomes, making objectivity provisional and relational rather than absolute. This challenges your intuitive sense of an independent reality. If measurement creates properties, then what you perceive as a stable, external world may be the product of countless interactions that selectively crystallize possibilities. The apparent solidity of matter, the definiteness of objects, and the consistency of physical laws are emergent consequences of these interactions, not inherent attributes of an independently existing universe. Delayed choice experiments further complicate the picture. Decisions made after a particle has entered an apparatus can appear to retroactively determine its prior state. Observation is not constrained to reveal what already happened. It can influence the history of a system. Reality is malleable, contingent on interactions, and fundamentally intertwined with observation. Even the most foundational scientific concepts, position, momentum, spin, and energy, are subject to this principle. They are not intrinsic attributes that exist independently. They are relational, arising from the specific circumstances of measurement. Every measurement is an act of participation in the unfolding of reality, converting a landscape of potentialities into an actualized state. The philosophical and existential consequences are profound. You are not merely witnessing the universe. You are entwined with its processes of becoming. Observation is an act of co-creation. Every interaction, every measurement, every conscious or unconscious detection contributes to the ongoing generation of the reality you perceive. In this framework, the classical assumption of an independent, objectively defined universe is provisional. The world exists in potential until it is interacted with, measured, or observed. Reality is not fully formed until you and all interacting systems participate in its creation, making observation a fundamental, active component of existence rather than a passive act of discovery. The universe, at its most basic level, is a participatory process. What you measure is not merely revealed, it is brought into being through your interaction with it. The world is not just out there waiting, it emerges moment by moment in response to observation. The act of seeing is the act of creating. 19. There may be no single objective universe. Different observers can describe the same quantum system in incompatible ways, yet all descriptions remain valid. This challenges the idea of a single, observer-independent reality. Instead, reality may be relational, existing only relative to a particular frame of interaction. You assume that the universe you inhabit is objective, the same for everyone, everywhere. A tree in a forest, a star in the sky, a particle in a laboratory. These exist independently of who perceives them. Classical physics reinforces this intuition, treating objects and events as fixed, universal entities. Quantum mechanics undermines it. At the deepest levels, reality may not have a single, absolute state, but a multiplicity of valid, observer-dependent perspectives. Consider a simple quantum measurement. An observer interacting with a particle records a particular outcome. Another observer, who has not interacted with the system, may describe it differently, still using the formal rules of quantum mechanics. Both accounts are internally consistent, yet incompatible. The state of the system is not a single, objective fact, but a relational property that depends on the observer's interactions. Reality is conditional, not absolute. This is not a failure of knowledge or perception. It is not an error in measurement or a limitation of instruments. It is the way the universe fundamentally operates. Quantum states do not exist independently of the systems observing them. Each observer constructs a version of reality contingent on interactions. What one sees as a definite outcome may be a superposition or an alternative outcome for another. The relational view extends the unsettling consequences beyond laboratory experiments. Your everyday experience of a coherent, objective world may be emergent. Macroscopic reality appears consistent because the interactions among countless systems enforce correlations, aligning perspectives sufficiently to produce agreement. But agreement is a statistical phenomenon, not proof of a singular underlying truth. At the foundational level, multiple versions of reality coexist, each relative to different observers. This perspective challenges your assumptions about causality, identity, and continuity. If reality is relational, then events do not possess intrinsic properties independent of observation or interaction. The facts of the universe are not absolute, they are contextual. Space, time, energy, and even the identities of objects are defined relationally, emerging from the network of interactions rather than existing as self-contained absolutes. Entanglement intensifies this ambiguity. Observers interacting with different parts of an entangled system may each perceive outcomes that are consistent within their own frames, but incompatible globally. Reality cannot be reduced to a single unified account. The universe does not contain one objective narrative. It contains many overlapping, interdependent narratives, each shaped by its own interactions. The philosophical implications are profound. Knowledge itself becomes a relational concept. To know something is not merely to access a pre-existing fact. It is to occupy a position in a network of interactions that defines what can be said to exist. The universality you assume in your observations, the idea that the world is the same for everyone, is an emergent property of shared context, not a fundamental guarantee. Even at large scales, this challenges notions of consistency. Cosmology, for example, relies on assumptions of homogeneity and isotropy, treating the universe as fundamentally uniform. Yet, if relational reality is fundamental, these assumptions are approximations valid only within particular observational frameworks. Beyond these frames, descriptions could diverge in ways that are coherent but mutually incompatible. In this view, the universe is not a single objective entity. It is a web of relationships, a tapestry of perspectives, each valid within its own frame. Observers are not detached spectators, but participants whose interactions define the reality they perceive. There is no absolute out there existing independently of observation. There are only overlapping, relationally defined realities, interwoven yet distinct, each a legitimate account of existence. Your assumption of a singular, shared universe is provisional. The objective world you inhabit is a construct emerging from interaction, a coherent pattern that masks a deeper multiplicity. At its core, reality may be less a fixed stage than a network of perspectives, each shaping and defining existence from its own vantage point. The universe, in essence, is relational, not absolute. 20. Information cannot be destroyed. Quantum theory implies that information is conserved even when matter collapses into black holes. This creates paradoxes where information appears both lost and preserved. The universe seems unwilling to forget anything, even as it transforms it beyond recognition. You assume that matter and energy can be destroyed or lost. A burning piece of paper turns to ash and smoke, its content seemingly erased. Yet, quantum mechanics suggests that the underlying information, the precise arrangement of particles, the quantum states, cannot vanish. Even when matter crosses the event horizon of a black hole, the rules governing quantum theory demand that the information encoded in its state must persist in some form. This principle challenges your intuitive understanding of impermanence. Destruction, erasure, and disappearance are familiar concepts. You burn, break, or bury things, assuming that with them goes the information they carry. Yet the universe enforces a deeper conservation. Information is fundamental, immutable, and indestructible. Physical transformations can obscure or scramble it, but they cannot annihilate it entirely. Black holes illustrate this paradox starkly. According to classical general relativity, matter falling into a black hole is lost to the outside universe. Its structure, identity, and history vanish behind the event horizon. Quantum mechanics, however, demands unitarity, the preservation of information. Hawking radiation, predicted to leak from black holes, carries energy but seems random, leading to the famous information paradox. How can information both disappear into the black hole and persist in the radiation that escapes? The tension between these perspectives is unresolved, highlighting the universe's insistence that nothing is ever truly erased. The conservation of information implies a universe that remembers everything, even if that memory is encoded in ways you cannot directly access. The precise quantum state of every particle, every interaction, is preserved in principle. Nothing is ever completely annihilated. Transformations can hide or disperse information, but the underlying data persists. Reality is, at its core, a ledger that refuses deletion. This perspective shifts your understanding of decay and change. When systems break down, it is not the information that disappears. It is reorganized, diffused, or entangled with the environment. Entropy and disorder describe the accessibility of information, not its annihilation. The universe does not forget. It only makes retrieval increasingly improbable. Even in apparent chaos, the quantum record remains intact, encoded in correlations that may be impossible to reconstruct, but are, in principle, conserved. The implications extend to causality and determinism. If information is preserved, then theoretically, the past is encoded in the present. The evolution of a system contains traces of its history. While practical retrieval may be impossible, the universe retains a complete record of events, a permanent imprint that links all moments through the conservation of information. The flow of time becomes less about loss and decay than about transformation and encoding. At the macroscopic scale, this principle manifests subtly. Broken objects, dispersed particles, and fading energy appear to erase structure, yet the information is not gone. It has been redistributed, entangled with surrounding systems, or transformed into different forms. Entropy increases, but underlying correlations encode the past. The universe may appear oblivious to destruction, yet it never truly forgets. This leads to a profound unease. Nothing you consider destroyed is ever fully lost. Every interaction, every transformation, leaves a quantum trace. The universe accumulates history, preserving it invisibly, encoded in ways beyond ordinary perception. Even black holes, the ultimate consumers of matter, cannot erase the informational content of what falls within them. In this view, the cosmos is a permanent archive. Information underlies every event, every particle, and every interaction. Destruction is provisional, forgetting is impossible. Matter may crumble, energy may disperse, and forms may dissolve, but the quantum record endures. Reality, in its deepest sense, is a conservatory of all that has happened, a network of information that refuses to vanish, indifferent to your expectation of impermanence. The universe, it seems, does not let go. Even in the most extreme transformations, it preserves the essence of all that has occurred. Nothing is truly lost. Everything is conserved, encoded, and remembered, waiting, in principle, to be reconstructed from the echoes of existence itself. 21. Consciousness may not be irrelevant. While not required by quantum mechanics, some interpretations suggest that consciousness plays a role in measurement. Even if this is ultimately false, the fact that the theory allows the question at all is unsettling. It forces you to consider whether mind and matter are as separate as they appear. You experience consciousness as an internal phenomenon, distinct from the physical processes of the world. Thoughts, perceptions, and awareness seem private, separate from the atoms, photons, and forces that constitute reality. Classical physics treats the mind as a byproduct of material interactions, an emergent property that does not influence the behavior of particles. Quantum mechanics, however, introduces ambiguity. In some interpretations, the act of observation is not merely an interaction, it is tied to awareness itself. Measurement is the process through which potentialities collapse into definite outcomes, and the question arises, what qualifies as an observation? In the Copenhagen interpretation, the role of the observer is central, though often understood operationally rather than consciously. The observer's measurement defines the state of a system, collapsing a superposition into a specific outcome. Some physicists, like Eugene Wigner, have speculated that consciousness may be essential to this collapse. While mainstream physics does not demand this, the mere possibility is profoundly unsettling. It suggests that reality may be interwoven with awareness, that the universe could be participatory in ways beyond mechanistic interactions. Consider the thought experiment of Schrödinger's cat. The cat exists in a superposition of alive and dead states until observed. What constitutes an observation? If an unconscious instrument records the outcome, is that sufficient? Or does consciousness play a role in resolving the superposition? The distinction is subtle, yet it exposes a conceptual gap between the physical and the experiential, a gap that quantum mechanics does not fully close. Even if consciousness is not literally required to collapse quantum states, the fact that the theory allows the question blurs the boundary between mind and matter. Physical systems are no longer entirely autonomous. Their properties may depend on interactions whose interpretation includes observation. The classical separation between subject and object, observer and observed, becomes provisional, contingent on how we define measurement. This idea challenges your intuitive sense of independence. You consider yourself a conscious agent interacting with a universe of inert matter. Quantum mechanics, in some interpretations, suggests the possibility of entanglement between awareness and reality. Consciousness may not merely perceive the world. It may play a participatory role in shaping the definite structure of events, influencing which potentialities become actual. The implications extend to identity, causality, and existence itself. If consciousness interacts fundamentally with the physical world, then the mind is not confined to an emergent narrative. It becomes part of the process by which reality unfolds. Each act of perception, however subtle, may be intertwined with the physical manifestation of states. The universe may not be entirely separate from experience. It may co-evolve with it. Even in everyday life, this principle resonates. Every measurement, observation, or perception is an interaction, a point where potential becomes actual. The mind, whether aware of it or not, participates in reality's ongoing construction. You are not merely an observer of a pre-existing world. You may be an active participant in determining which possibilities are realized and which remain unrealized. The possibility that consciousness is relevant, even minimally, undermines the classical materialist assumption that mind and matter are entirely separable. It forces you to confront the unsettling thought that awareness may be a non-trivial actor in the unfolding of the universe, entangled with events in ways that physics allows but does not yet fully explain. In this framework, reality is not a passive backdrop for your experiences. It is a system in which consciousness and matter may be interdependent, each defining the other in subtle, unresolved ways. The mind is not outside the quantum world. It may be woven into its very fabric, influencing outcomes, collapsing possibilities, and participating in the creation of the reality you take for granted. Consciousness, then, may not be irrelevant. At the edge of quantum theory, the distinction between observer and observed, mind and matter, becomes ambiguous. You are not merely witnessing the universe. In some interpretations, you may be implicated in the very act of its becoming, entwined with reality in ways that challenge the most basic assumptions about separation, autonomy, and existence. 22. The universe may be fundamentally random. Determinism once promised that knowing the present would reveal the future. Quantum mechanics replaces this with intrinsic randomness. Some events have no reason beyond probability. The universe does not always explain itself, even in principle. You assume that the world is orderly, that patterns emerge from cause and effect, and that every effect has a reason grounded in prior states. Classical physics reinforced this view. If one could measure the position and momentum of every particle precisely, one could, at least in theory, predict all future states. Quantum mechanics, however, dissolves this certainty. At its core, reality includes events that are genuinely random, whose outcomes are determined by probability, not hidden variables or deterministic laws. Consider the decay of a single radioactive atom. You cannot predict the exact moment it will emit a particle. You can calculate a probability distribution, but the individual event is fundamentally unpredictable. This is not a limitation of knowledge or measurement. Quantum randomness is intrinsic. The universe permits occurrences that happen without a cause in the classical sense. The very notion of explanation, as you understand it, reaches a boundary. Some events simply happen. Randomness in quantum mechanics is not confined to obscure laboratory experiments. It underlies the fabric of reality. Particles in superposition do not choose a definite state until observed, and the choice is probabilistic. The wave function describes possibilities and their likelihoods, but no underlying mechanism determines which outcome is realized. The world, at its most fundamental level, is open-ended, a theater in which chance plays a decisive role. The implications extend far beyond physics. If the universe is fundamentally random, then causality, as you intuitively understand it, is provisional. The arrow of time, the unfolding of events, and the trajectory of your own life are subject to outcomes that cannot, even in principle, be fully predicted. Your attempts to forecast, control, or explain are constrained by intrinsic indeterminacy. Certainty is an emergent illusion, valid only in aggregated systems where probabilities average into apparent determinism. This randomness also reshapes your understanding of lawfulness and pattern. Even in a universe governed statistically by rules, the specific realization of events contains indeterminacy. A single quantum fluctuation can cascade, influencing larger systems in ways that cannot be prefigured. Order emerges, but unpredictability remains fundamental. You inhabit a world that is coherent at scale, yet underpinned by the unexplainable at its foundation. Even macroscopic phenomena, when traced back to their quantum constituents, inherit this randomness. The particles in your brain, in the air around you, in the stars above, all operate with intrinsic probabilistic behavior. While large numbers smooth out outcomes into patterns that appear deterministic, the foundational layer is stochastic. The universe is not a clockwork machine, but a probabilistic process, endlessly generating possibilities, collapsing them into actualities without invoking deterministic necessity. Randomness at this level challenges the assumption that the universe is intelligible in the classical sense. Explanations and predictions rely on statistical regularities, but the underlying reality contains events without deeper causal justification. Some phenomena occur not because of antecedent conditions, but because probability dictates that they can. Chance is baked into the structure of existence, unavoidable and irreducible. This realization has unsettling philosophical consequences. Free will, agency, and moral responsibility are cast in a different light. Even the predictability of natural events, the consistency of laws, and the orderliness of reality are provisional, contingent on probabilistic patterns emerging from randomness. At its deepest level, the universe does not offer reasons for everything. It allows certain events to occur simply because they are possible. In this framework, existence is not a deterministic narrative, but a constantly unfolding ensemble of possibilities. Some outcomes are determined by interactions, some by statistical regularities, and some by pure chance. The universe, in its essence, is not always explicable, not always predictable, and not always bound by reason as you understand it. Reality contains true randomness, and in this randomness, the world becomes a place that does not always explain itself. You inhabit a universe that is partially ordered, partially lawless, and fundamentally probabilistic. Certainty is a feature of scale, not a guarantee of the underlying structure. At the deepest level, chance reigns. Events occur because they can, not because they must, revealing a cosmos that is less clockwork and more open-ended, indifferent to the human desire for total explanation. 23. Mathematical structures may be more real than matter. The uncanny effectiveness of mathematics in describing quantum phenomena raises the possibility that mathematical relationships are more fundamental than physical objects. Matter may be an expression of abstract structure rather than the other way around. You assume that the world is primarily composed of things, particles, fields, and forces. Mathematics, in this view, is a tool invented to describe these entities. Yet the success of mathematical frameworks in predicting and explaining the behavior of the quantum world is profound, bordering on mysterious. Equations written on paper, purely abstract constructs, consistently yield predictions that align with experiments to astonishing precision. This suggests that the underlying reality may be structured more like a mathematical object than a collection of material parts. Quantum mechanics exemplifies this. The wave function, a mathematical entity, contains all possible states of a system. It is not merely a convenient description. It evolves according to deterministic equations, and its predictions are borne out in experiments with remarkable fidelity. The particle you observe, its spin, position, and momentum, may be secondary to the mathematical relationships that define its potential states. Matter itself appears as an emergent manifestation of a deeper, abstract structure. Consider symmetry principles in physics. The conservation laws that govern energy, momentum, and charge are consequences of underlying mathematical symmetries. No particle knows to conserve energy. It behaves in accordance with the structure of the equations that define it. The universe, in this sense, obeys mathematics because mathematics is the fundamental framework from which all properties emerge. Physical objects are shadows cast by these underlying abstract relationships. This view is reinforced by the predictive success of quantum field theory and the Standard Model. Particles, forces, and interactions emerge naturally from mathematical structures and group theory. Equations dictate the possibilities of existence before any material manifestation. The universe is astonishingly well described by math because, in a fundamental sense, it may be mathematical. Matter, then, is derivative, a pattern realized from deeper abstract rules. The philosophical implications are profound. If mathematical structures are more real than physical objects, then reality is less about stuff and more about relationships, patterns, and forms. Existence is defined not by matter occupying space, but by the coherence and consistency of abstract structures. Your body, the chair you sit on, the stars in the sky, they exist because the underlying mathematical framework allows for configurations that manifest as stable, observable entities. This perspective destabilizes assumptions about tangibility and concreteness. You interact with what you call matter, yet at the deepest level, it may be a projection of abstract rules. Quantum superpositions, entanglement, and interference patterns, all phenomena that seem counterintuitive, are natural consequences of the universe's mathematical substrate. They are not strange because the world is weird. They are inevitable if matter is secondary to structure. Even the constants of nature, Planck's constant, the speed of light, the fine structure constant, gain a new significance. They are not arbitrary features of a physical world, but parameters within a mathematical architecture that give rise to observable phenomena. Change the structure, and the universe itself would be different. Reality, in essence, is the manifestation of these abstract relationships. This also reframes the concept of laws of physics. They are not imposed rules on pre-existing matter. They are the inherent consequences of mathematical reality. What you perceive as physical necessity is simply the logical outcome of consistent structures. The universe is not a material arena governed by laws. It is an instantiation of mathematics. The unsettling implication is that the world you perceive as concrete, solid, and material is, at its foundation, abstract and intangible. Matter is emergent, not fundamental. Reality is a tapestry of mathematical relationships, and what you call existence is the projection of these structures into forms accessible to observation. If this view is correct, the universe is less a collection of things and more an intricate mathematical object. The physical world is an expression of deeper abstractions, and the solidity you take for granted is a manifestation of patterns that exist independently of any material instantiation. At the most fundamental level, reality may be composed not of atoms and particles, but of pure mathematical relationships, structures whose existence does not depend on space, time, or observation, yet which give rise to all that you experience. 24. Reality may be self-consistent but incomprehensible. Quantum theories work astonishingly well while resisting intuitive understanding. This suggests that reality may not be obligated to make sense to human cognition. Comprehension becomes optional, not guaranteed. You assume that the universe is intelligible, that the patterns you observe can ultimately be grasped by reason and logic. Science itself is founded on this belief, that with sufficient effort, observation, and thought, the principles governing existence can be discovered. Yet quantum mechanics consistently undermines this assumption. Its equations yield predictions of extraordinary accuracy, yet their implications are counterintuitive, defying common sense at every turn. The world behaves in ways that human cognition struggles to accommodate. Consider wave-particle duality. Electrons behave simultaneously as particles and waves, yet classical logic insists they must be one or the other. Entanglement allows instantaneous correlations across vast distances, violating the intuitive constraint of locality. Superpositions permit mutually exclusive states to coexist until observation. These phenomena are mathematically consistent, experimentally verified, and yet profoundly alien to perception. Reality functions according to a coherent internal logic, but this logic is one your mind was not designed to intuitively process. The incomprehensibility extends to time, causality, and identity. Events can be influenced retroactively. Cause and effect may not follow a singular direction, and objects may lack intrinsic properties until observed. The universe may be fundamentally relational, probabilistic, and context-dependent. Each successful quantum theory confirms that reality is internally consistent, yet the patterns it produces are not necessarily aligned with the heuristics and expectations evolved in a macroscopic, classical world. Your cognitive toolkit is ill-equipped to grasp the full consequences. Mathematics offers a bridge, but even it has limits. Equations provide precise, predictive frameworks, yet the results they generate can be startlingly opaque. Schrödinger's cat is alive and dead. The vacuum is not empty, but seething with virtual particles. Information cannot be destroyed. These concepts are internally consistent within the mathematical formalism of quantum mechanics, but they stretch your intuitive sense of possibility and impossibility. Logic is satisfied, comprehension is not. This suggests a deeper principle. Reality is not obligated to be comprehensible. Coherence and consistency do not imply accessibility. You may never fully grasp why the universe allows superpositions, or why entanglement is instantaneous, or why the vacuum teems with ephemeral activity. The universe may be constructed from principles and structures that operate independently of human intuition. Your understanding is contingent, limited by the evolutionary development of your cognition, yet reality itself remains unaffected by these limitations. The implications are both philosophical and existential. If comprehension is optional, then certainty is provisional, and human reason is not guaranteed dominion over the cosmos. Knowledge becomes a local approximation, constrained by scale, context, and cognitive architecture. The universe may be entirely intelligible at some abstract level, or it may be fundamentally beyond human grasp, its self-consistency maintained without regard for your capacity to make sense of it. Even scientific methodology must be reconsidered. Experiments, observations, and models provide reliable predictions, yet they do not necessarily yield intuitive understanding. You can manipulate, anticipate, and calculate outcomes without ever feeling that you understand them. Comprehension is a luxury, not a requirement for functioning in a quantum universe. Success does not equate to insight. At the deepest level, reality may be a system of internal logic, precise, lawful, and coherent, but fundamentally alien to perception. Your mind imposes patterns and seeks causality, but the universe does not conform to these demands. Consistency exists independently of comprehension, and what you perceive as paradox, weirdness, or impossibility may simply be the gap between human intuition and the underlying structure of reality. In this framework, the universe is self-consistent, but potentially forever incomprehensible. You inhabit a reality that functions according to rigorous rules, yet those rules may never yield to your intuition or reasoning. The cosmos operates flawlessly, independent of human expectation, leaving comprehension optional, provisional, and never guaranteed. The world is orderly, yet its order may lie entirely beyond the horizon of understanding. 25. You may be experiencing a simplified interface. What you perceive as reality may be a filtered representation optimized for survival, not truth. Quantum mechanics hints that the underlying structure is too complex, too contradictory to be experienced directly. What you see may be a useful illusion layered over something far stranger. You assume that your senses provide a faithful map of the world. Your eyes see objects, your ears detect sound, and your brain assembles a coherent narrative from these inputs. This narrative feels continuous, stable, and reliable, and it forms the basis of your understanding of space, time, and matter. Yet quantum theory suggests that what you perceive is not reality itself, but a processed, constrained interface. The true underlying structure of the universe may be far more intricate, paradoxical, and counterintuitive than your perception allows. The concept of a simplified interface arises naturally from the gap between the macroscopic world you inhabit and the microscopic world quantum mechanics describes. Particles exist in superpositions, entangled across vast distances, and behave in ways that violate classical expectations. To navigate such a world directly, without filters, would be impossible. Conscious experience, and perhaps even evolutionary necessity, favors a version of reality that is coherent, stable, and functional, rather than accurate at the quantum level. In this view, perception is a kind of graphical user interface. The sensory data you receive are translated into a simplified model your mind can process. Solid objects appear continuous, time flows linearly, causality seems strict. Yet beneath this interface, reality is probabilistic, relational, and context-dependent. Your mind does not access the full quantum state of the universe, nor does it experience entanglement, superposition, or the vacuum fluctuations that constantly occur around you. It perceives only what is necessary to survive, act, and predict reliably in the macroscopic world. Quantum phenomena provide hints of the interface's limitations. Superposition, measurement-dependent states, and entanglement demonstrate that the universe contains layers of complexity that your direct perception cannot access. The deterministic classical world you experience is an emergent representation, a rendering of deeper probabilistic structures. The rules of this rendered reality are designed for coherence and utility, not for exposing the underlying strangeness. What you see is useful, not ultimate. This raises unsettling philosophical implications. If perception is inherently filtered, then your experience of time, identity, space, and causality may be provisional. Continuity of self, the solidity of objects, and the linearity of events could be artifacts of the interface rather than intrinsic features of the universe. The world you inhabit is a model constructed by your senses and cognition, one that simplifies, smooths, and resolves contradictions to create a comprehensible experience. Reality in its full form may be far more complex, contradictory, and alien. Even the laws of physics, as you perceive them, may be emergent properties of the interface rather than fundamental truths. Constants, forces, and interactions that appear fixed and universal may be approximations of deeper dynamics too intricate for direct perception. The world is internally consistent within the interface, but it may conceal vast layers of phenomena beyond comprehension. What you call reality is, in a sense, a practical illusion, optimized for interaction and survival rather than truth. This concept challenges your confidence in experience. Your senses, your intuition, and your reasoning operate on a version of the universe tailored for functionality. You cannot directly access the underlying quantum structures, and attempting to do so would be like trying to navigate a three-dimensional object using only a two-dimensional projection. The map is coherent, but it conceals the full territory. In this framework, reality is both familiar and alien. You inhabit a version of the universe designed for perceptual ease and cognitive survival. It appears orderly, stable, and comprehensible. Yet beneath this veneer lies a domain of astonishing complexity, paradox, and indeterminacy. What you experience is a simplified interface, a useful illusion layered over the fundamentally strange, probabilistic, and entangled fabric of existence itself. You may never perceive the full depth of reality directly. What you see is optimized for coherence, not completeness. The universe, at its most fundamental level, remains beyond immediate apprehension, inscrutable to intuition, and infinitely more intricate than the reality your senses render for survival and understanding.